All right, so here's the recording for today. The mic is on. I totally forgot to start recording with cisp440, the next class on Tuesday. And it turned out to be one of the more important lectures. So that. All right, so let's restore this. And we'll check whether the lecture on Tuesday for this class is uploaded or not. Okay, so today is the 16th, so we're looking at the 14th, and it is not uploaded. Okay, so let me see if I have it, and if I do, I can upload it right now. Yep, we do have that. But it's called MP3 instead of MP4, so that might be just a that might be just the audio of it. Yeah, it certainly looks that way. It looks like it might be just the audio. Okay, let me open it with, let me check whether it is the case. Okay, so this is a good time to demonstrate the power of Linux, okay? So do we know whether it really is just MP3 or is it just a file with the MP3 extension, okay? So in Linux, there's a program called file, and you can use file to check the type of something. So this is 2017-0314 Pi Day, cisp440.mp3. And it says it is just an MP3. It's a MP3 file. So you guys got the audio portion of that, but not the video part.
Was that for last class?
Yeah.
Well, I mean, there wasn't much done on the screen.
That is correct. Yep. But I'm not sure. Can I upload just the audio portion to YouTube or?
Again, it'll just be a black screen.
Okay, so we can do that. Let me try that then. Okay.
You could ask the students for the pictures they took of the whiteboard during your lecture and use that in the video to show what's going on.
I can try to stitch everything together, right?
Yeah. Or just be lazy.
Well, the interesting part is in the mobile programming class, there was one student whose project this semester is going to be a mobile app, so that you can use the mobile app to both record the audio portion and also automatically snap a picture. So you don't even have to click a button or do anything. You just have to hold it up to the screen, and it can automatically recognize the frame of the projector. And when everything is in focus, and everything is inside the frame, it will take a picture and then timestamp it.
Huh.
And then he also wants to make it, well, depending on whether he has enough time or not, he wants to make it so that people in the same class can crowdsource stuff. So you guys take different pictures, and then all of those pictures will be uploaded, and a program online will stitch all of these things together. So even if you take each person takes 3 pictures, okay, but at different times, so you as a whole class you will still have about 100 pictures all together uploaded at different times, and then all of those pictures will be sequenced according to the actual timestamp. So that's that may be an interesting app for people to use, except for certain math classes where your professor does not let you use a camera to take pictures of the whiteboard. Okay, so this is being converted, and I'm just curious, whether it will upload or not. Okay, so the file you uploaded contains only audio and no video, and I want to convert the audio track to a video file type. So it doesn't do it automatically. I guess I can do it, after the fact, later on. Okay, well, we'll deal with that later. Okay, so the homework assignment is postponed, I think, right? Yes. To next Tuesday, and I forgot about that. So I'm giving you a new homework assignment. So it's overlapping a little bit. But the new homework assignment is easier, and it kind of goes along with the other homework assignment. So I'm gonna give you like kind of like two homework assignments that are going on at the same time because they're closely related. I don't think it's going to, the second program is actually a whole lot easier, long class. This is cisp440. Okay, so when you go to probability distribution, down here, discrete probability, not distribution. There's a second homework assignment called Count Unique. And Count Unique is a program that is actually a little bit easier. It is not recursive. So what you do is you want to process the output from the previous assignment, which is the one that you're still working on, that is due on Tuesday. The purpose of this program, the new program, is to count the number of unique values on each line. Okay? So the sample input is like this. If this is the actual input, then the output is going to be 3213 because on the first line you have 3 unique values. Each character is considered individually. On the second line you have 2 unique values, and that's why the output is 2. On the third line you only have 1 single value, and that's why the output is a 1. And then on the last line, once again, we have 3 unique values, so the output is a 3 in this case. Okay, and that's your second program. I think the second program is significantly easier than the one that you have to generate all the possibilities. So that's why I'm not gonna change the due date of this one. So this one is due 1 week from today, which means you have 2 extra days after the due date of the one that was supposed to be due today, but extended to next Tuesday. All right. Are there any questions about this particular program? The new one. No particular question? Yep, go ahead.
I thought I had something. I didn't.
Okay, so in terms of limitations, it will still be limited by up to 9 possibilities per trial. So if you need to plan for that, you can plan for only having to deal with up to 9 unique values.
Okay, so this program, is it going to output both the results of the experiment and the number of unique?
No, this is the standard input. So this is what you present to the program through standard input or C-in,
gotcha.
and this is the output of the program or C-out.
So we're inputting into this program what our output would be from the previous
Correct.
one? Okay.
Yep. Sort of. Because in this case, this is standard input, so you're not going to give it a file name.
Gotcha.
Yep. Mm-hmm.
Did you say that, I'm sorry, I was kind of sidetracked when you was asking that question, but I think, were you asking about how if there was like more than 10 choices, then it would be a 2-digit number?
You can only have up to 9 choices according to the homework assignment.
Oh.
So for each trial, for the initial trial, you can only have 9 individual possibilities.
Is it fine?
0 to 8, basically.
Is it fine if it goes above that?
Sorry?
Is it fine if it does beyond that?
If you go beyond that, then how are you going to represent those things? How do you print it out? Because you only get 0 to 9, which is 10 possibilities, which is still just 1 more than what I put. I put a limit of 9. If you have like 16, then you have to kind of do a hexadecimal thing, 0 to 9, and then A, B, C, D, E, F.
I had like a different out before. I didn't expect you to give us one, so I had worked on it prior, and I don't know, it was worth it.
So,
I'll take a look at it.
Well,
Okay.
to answer that, the way I did it in mine, I just put a space between each trial.
oh, so you use a space between
Yeah, so
the
if you
trials.
went up to 16 or
Gotcha. Okay.
16 space.
In that case, when you process this, you have to process it differently. Okay, how many people put a space between the trials?
Just to test it.
Okay, how many people have finished the program? Okay, so many people did not put a space in between. Okay.
I've got a version that doesn't do it anyway, so I'll just use that one.
Yeah, put a switch in your program, so or put it into the configuration file. Just add 1 more line whether to have a space to separate the values or not. Okay. Okay, cool. Any other questions related to SpaceGen, which is the program to generate all the possible outcome of experiments, or this particular program, which is counting the number of unique values per line? Any questions about any one of these two programs? Okay, if there are no questions, then we'll continue to talk about the terminologies, because we're going back a little bit to talk about what is considered discrete, and also what is a probability space. Okay, so let's talk about the probability space, which is just a definition of terms in this case. There's no derivation yet at this point. So a probability space, which is an entire space of, there are three components to this. Okay, the first component is omega, which is not to be confused with omega in propositional calculus, because in propositional calculus, omega is used to represent the operators, the connectives. In this case, omega is a set of all the possible experiment outcomes of what is being modeled. Each element in omega represents a possible output of an experiment. Recall that an experiment is a sequence of trials, and each trial has its own set of outcomes. So this is great because it relates directly to your homework. Each line of your program is an element in omega. Is that okay? So I'm hoping, because you're writing the program, or at least you should have started to write the program. So at this point, when I say, each line of your program is representing an element in this omega, and the entire output file of your program is omega itself, then you can start to, then you can link the program itself to the concept of omega, or the probability space. Now this one is a little bit more kind of funky. It's kind of like F, okay, but it's a kind of funny looking F. It's a set of events. An event is a subset of elements of omega. The union of all the elements in F should be omega itself. That's the only requirement. Okay, so let's go ahead and look at this one more time. F is a set of events. An event itself is a subset of elements of omega, or you can just say an event is a subset of omega. The union of all elements in F should be omega itself. Okay, so are there any questions about this particular point? Can I do something like this? Okay, can I make that funny looking F? Okay, so let's make the funny looking F here. Can I say that is omega? Would it still fit the terms that we use to describe F? The answer is no. We're missing one little thing. Because F is supposed to be a set of events, right? In other words, it is supposed to be a set. Each event is a subset of omega. Now, is omega a subset of omega?
Yes.
Yes. Is it a proper subset of omega? No. Okay, but I only said subset, not proper subset. So it's okay for omega to be an element of F. Am I saying that omega is an element of F? No, I'm saying omega is F. So this is not okay, but this is. Is that okay? So can everybody see the difference between F equals to omega as opposed to F equals to the set that has omega itself as an element? They are different concepts because in one case we have one set being exactly the same as the other set, which means they have exactly the same elements. In the second case, we have a set that is a set of sets. So each element within F is a set itself. It just so happens that the union of all of these sets in F, they have to come back to omega when you have a union of all of those elements. Is that okay? All right. What about this? Can F be omega itself and the empty set? Would that meet all the requirements for F? This is another case to test whether you understand that statement or not. Yes, okay? Because when you take the union of omega and the empty set, what is the result of that union? Omega itself, okay? So it meets the second requirement. And then the first requirement is it has to be a set of subsets of omega. Is omega a subset of omega? Yes. Is the empty set a subset of omega?
Yes.
Yes. So it meets that requirement as well. So it is okay to be like that. Okay. So these are just two examples to illustrate, what can be in F, or what can be a single event and what is a set of events. So the last one is the actual function. It's a function that maps events to their probabilities. So in this case, you can see that Fp is a function. The domain is the set of the events, and it is mapping each event, which is a subset of omega, to a particular real value between 0 and 1 inclusively. Is that okay? All right. So now we take a look at buying a lotto ticket. So in the case of buying a lotto ticket, omega would be all the possible combinations of numbers. Now we are dealing with a simple lotto game, not the one with a mega number and stuff like that. So this is all the possible combination. F is a little tricky depending on the player. If we assume a player can purchase multiple lotto tickets, then F can be the power set of omega. In the simplest case, it can be just a particular outcome. So it depends. So the way you set up the events depends on what do you want to know. Okay, I can also set up F so that each element of F is basically a subset of omega for a particular price. Does that make any sense? No? Okay. So let's say I'm the organizer of Lotto. Okay. So what I'm interested in is, okay, according to probability, what is the amount of payoff for each week? Okay. It seems to make sense that I might need to worry about that sort of thing, right? So when you look up the Lotto game, the Lotto game and look up a particular Lotto, and keep going to the wrong place. Huh? So California Lotto. Okay, it's callotto.com. So in callotto.com we have different types of Lotto games, and let's pick one that is easy to model. Click on games. Let's pick Super Lotto. In Super Lotto, you have different ways of winning. So let's take a look at the winning. Since I don't play Lotto, I have no idea what kind of prizes or how you can win the Lotto game. Official rules. Purpose, term of promotion. Nope, that's not it. Okay. Buy 5 plays, get 1 free quick pick. Buy 10 plays, get 2. Okay, that might be a little bit harder from our perspective to model. So let's pick something else. Mega Million, Super Lotto Plus. How to play. There we go. And does it tell you how to win? That's the question. There we go. Okay, this is what I'm looking for. So the winning, if you have all 5 of 5 numbers and match them, the mega, that's the jackpot. Okay, that's one way to win. The second way to win is to match all 5 numbers, but not having the mega number to match. So that's only 5 out of 5. You can also match 4 out of the 5 numbers and also the mega number, or you can just match 4 out of the 5 numbers. So you can see that there are many ways to win this particular game. So in this case, in your F, the subsets, the elements of F, each one can be a set of the winning combinations for a particular price. Okay. Okay, I'll give you one actual solid example. So I'm going to use a mouse pad here. So, mouse pad. Okay. How would you represent a particular winning number for Mega Lotto? how many numbers does it have, and also, is it a single set or is it a two-tuple, or what kind of thing is it? How do you represent the actual winning number for Mega Lotto? Okay, so according to this game, you have to pick 5 lucky numbers from 1 to 47, and then one mega number from 1 to 27. The first 5 numbers that you pick, it is the combination that matters, and then the mega number is completely independent to the first 5 numbers. So how do you represent the current winning number? For instance, if you go to past winning numbers, okay, last week, okay, so for last week the winning numbers are these 5 numbers, and then the mega number is 1. So what kind of concept have we talked about in this class that we should use to represent the winning combinations? Okay, so at the top level, is it a set or is it a two-tuple?
It's a set.
It's a two-tuple with a set inside and a number on the second part. Okay, so if you look at this particular winning number and the mega number, the way we can represent this, okay, let me see if I can scroll this. Yep, there we go. So the way to represent that is going to be a set of 31, 13, 36, 34, and 44. It is a set because the order does not matter. But on top of this, we're going to use a two-tuple so that we can also integrate the one which is called the mega number into this entire thing. Is that okay? I mean, is that making any sense? Okay, so this is one possible outcome. So this is a possible outcome of Mega Lotto. Is that okay? All right, so let's say this is the actual winning outcome. Okay, so we'll qualify this as our winning outcome. And we want to look at our F, which is a set of events. What events are of particular interest to us? And let's say I'm the organizer of Lotto. Okay, so I want to worry about, what are the chances, or what tickets are winning tickets, right? So we only have one single winning ticket that is winning the jackpot. So this thing, which is a set that is only consisting of one single element in this case, which is 31, 13, 34, 36, 34, 44 as a set of 1, and then close the paren because it is a two-tuple, close the set notation. This particular set here, I'm going to borrow the C notation here for starting to have comments. This is our jackpot. Okay? It is a particular set, but it only has one element because there's only one ticket that is supposed to win the jackpot. Is that okay? So the next thing I want to do is to find out, okay, what about not the jackpot, but the next best prize? Does anyone remember the next best prize for Super Lotto Plus?
You get 5 numbers and the mega number?
Not matching the mega number, but only the first 5 numbers, right?
If you get 4 out of the 5 and the mega.
Actually, the next best one is matching all 5 out of the 5 numbers, but not matching the mega. Okay? So how many elements do you think is in that particular set, and what do you think they look like?
2.
No,
So
there are.
with a set in it, but the set only has 4.
Yeah, it's a two-tuple.
5.
Each one is a two-tuple. Very good. Okay, so inside the two-tuple, what is the first thing in the two-tuple?
It's 4
The
numbers.
winning 5.
The same set, right? The same 5 winning numbers. Okay, cool. So we have 31, 13, 36, 34, 44 as the first item of the two-tuple because we still need the 5 numbers all to match. Okay, what about the second one?
0.
Cannot be 0, okay, because they don't have a ball numbered, 0. Can it be 1? No, because 1 will get you the jackpot. Okay, this is the second tier winning, so it can start with 2. Okay, it can start with 2. Sure. Okay, this is one of the many. And what would be another possibility here? 3. Yep. Okay, you guys are getting it. How about the next one? 4.
All the way to 40, all the way to 27.
Yep, exactly. All the way to 27. Very good. So we just say dot 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 all the way to 27, and you can see that the one that is missing is the jackpot, because the jackpot is its own set. Okay, so this one is, how do you call that? Oh, it doesn't have a particular name. It's just all 5 of 5. Okay, there we go. So can you imagine the next set? What do you think that's going to look like?
4, 5, and a jackpot.
Yep, exactly. Okay, so if you're only matching 4 out of 5 and a jackpot, you know it is a 2-tuple, and you also know the second item of the 2-tuple has to match the one of the jackpot. So we know it's going to be 1. The second item has to be a 1. Yep.
So you have all 5 and 5 listed as one thing, right? Would you consider that one element of omega, or each individual set part of omega?
Okay, so it has to do with the nesting of the parentheses and the curly braces. This is one element of F. But this thing, what I'm highlighting here, is a subset of omega. Because omega is representing all the possible tickets that you can actually purchase. Is that okay?
Okay.
So these are the tickets that will get you all 5 of 5. So the next tier down, we will have a lot more tickets, because in this case, I can have 31, 13, 36, 34, 40, and something that is other than 44. Okay, can be 1, yes, it can be 1, 2. So this can be 1, can be 2, all the way up to 12. Okay, we skip 13 because 13 is already in this set, and then 14 all the way to 30, and then from 32 to 33 we have to skip 34, and then 35 kind of in by itself, 37 all the way to the last number. Okay, is that making any sense? Okay, so we'll go ahead and just kind of list it out a little bit here. Okay, so the next one up, I'm just going to use this particular pattern here, 36, 34, 2, and we still need the mega number to match, because that's the qualification of this. But then we also have a whole bunch of other ones too, because I can also have the 31 itself not matching, but everything else being matching. So that means the 1 goes here, and then we have 13, 36, 34, and this one actually does match, which is a 44. And then the 1 over here, dot dot dot. Okay, there's a dot 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 here too. Okay, but are you guys getting the idea? What kind of elements is going to be in this particular set? Okay, every single ticket, every single Lotto ticket that will get you the 3rd tier prize will be in this particular set. So I'm only structuring this F this way because my interest is to figure out how many jackpots are we dealing with, how many 5 out of 5 are we dealing with, how many 4 out of 5, but with the special number matching are we dealing with, because I need to do some financial planning. I need to find out how much money do I need to plan as payoff. Is that making sense? Making any sense? Okay. But when at the end of the day, after you have all these sets, okay, each one representing a particular way to win the Lotto, I still have something else that I need to include here. In other words, I will have one set to represent the jackpot. It only has one single element. I will have one set to represent all 5 of 5. There are 26 of them, because the 27th one is the one that wins the jackpot. And then how many do we have here? Any 4 out of the 5 numbers, and then the mega number. What kind of number are we dealing with here? Okay, so let's go back and kind of look at the rule of the games first, because we need to know that the first 5 numbers can be anything from 1 to 47, but it is chosen without replacement. Okay, so if that is the case, how many tickets, okay, out of all the possible tickets, can match 4 out of the 5 numbers of the winning numbers, and also match the mega number. How many tickets would actually fit that requirement? How do we come up with that number? Okay, so let's go ahead and scroll this down to the point where it is below the text, just below the text editor, and then I go back to the text editor to do some calculations. Okay. So this is just a totally separate thing. The number of any 4 of 5 and mega. How do we figure this out?
36 times 5. 36 times 5 of those combinations. If you could take just one of the numbers and then 46. You do 46 combinations, like where it's 4 of them, and then one, like when one's wrong, and then make one right, and 46 more. Where
Well, the way I go about doing this is to think about it and go like, okay, we need to match 4 out of the 5 numbers of the 5 winning numbers, right?
But and
Okay.
the five numbers can be the numbers 1 to 47. But one of the numbers is used as the right number, so you ignore that one. And then that means they give you 46 in each slot. That it could be as long as it's not the right one, and do that. Yeah. Oh, sorry, no. Each slot's independent, and the numbers don't repeat. That makes it
Right. So what we are dealing with here is to count this first. Okay? We have to first think about, okay, how many ways can we choose 4 things out of 5? Why choose 4 out of 5? Why is this number particularly interesting to us? Why is it important?
we need correct.
What is the 5 representing?
The 5 represents all of them.
All the options.
All of the options, the 5 winning numbers, right? So I'm already staring at the 5 winning numbers, 31, 13, 36, 34, 44, okay? And I'm thinking about, okay, but I only want to pick 4 out of these 5, because the last one has to be non-matching, cannot match one of the winning numbers. So I need to figure out, okay, how many ways can I pick from the set of 31, 13, 36, 34, and 44, so that I only have 4 out of the 5 winning numbers. Okay, so 5 choose 4 is, I cannot remember. I mean, it doesn't really matter. Okay, because I can just leave it away as a combination. And then what do we need to do? We have to pick one of the non-winning numbers. Let's call those losing numbers. Okay, so how many ways can I choose a losing number? How many losing numbers do we have to choose from? There are 47 numbers to begin with, and everything is chosen without replacement. So after I have chosen 5 winning numbers, how many numbers do we have left? 47 minus 5 is 42. Okay? So we have 42 losing numbers. And out of the 42 losing numbers, I just need to pick one of them, in this case, right? So I just say, oh, okay, we can do that. We can choose 1 out of 42 of the losing numbers. Multiply these two, because the first one deals with the 4 winning numbers, and then the second one deals with the 1 single losing number. Yes?
So wouldn't it be 43 losing numbers because we only want 4 winning numbers, we want 5 winning numbers?
No. It's 42 losing numbers because there are 5 numbers designated as winning numbers, right?
Yeah.
And we have already chosen 4 out of the 5 winning numbers. The 5th number has to be one of the non-winning numbers, meaning it has to be one of the other 42 numbers. I cannot pick the remaining winning number that I did not choose earlier. Okay? So, but there's a particular reason why I choose to use 5 choose 4, which is actually 5. Yes, and also there's a particular reason I choose to say 42 choose 1, which is actually 42. Okay, because there's a pattern that I'm trying to develop here. Okay, and then I have to say, how many ways can we choose the winning number? There's only one winning number out of 27, I think. So this is that times 1. Okay. So when you do this calculation, that should match this number here, okay? All 5 of, no, excuse me, the other one. So we should be able to, we should be calculating this particular value, or this is 1 in, which means we're actually dealing with the reciprocal of that. Okay, so let's do some calculations, and we'll use, oh, I don't know. Do you want to use Google document, or do you, yeah, let's use Google document, because then I can share the document with you guys, right? Which is always good. Okay, so we'll go to apps.losreels.edu. This is another reason why I like to use Linux in these classrooms, because I get to keep all my bookmarks, I get to keep all my cookies, so I don't have to sign in every single time. There we go. So in the shared folder, I'm going to create a new document. It is a new spreadsheet. And I'll just quickly rename that to Super Lotto Plus. Super Lotto Plus. Okay. So this time, I'll use the third row to represent this, okay? Because we're dealing with 4 out of 5, and we also want, I just need to find out what is the terminology, and mega. Okay, so there we go, and mega. Okay, so the calculation is combin 5 of 4, 4 out of 5, and then combin 1 out of 42, right? And let's get rid of that paren here, times 1, and it's 210. In other words, out of all the possible tickets, 210 tickets would win that particular prize. But how many tickets do we have in total? Okay, I'm gonna use all the way down here, okay? Total number of unique tickets in Super Lotto Plus. Okay, what do you think that number is gonna be? Okay, once again, it has to do with combination and stuff like that. Okay, so let's deal with the 5 numbers first. Okay, the 5 winning numbers. You are choosing how many out of how many? You're choosing 5 out of, let's read the documentation here. So how to play will tell you the numbers. So pick 5 lucky numbers from 1 to 47. So you're picking 5 out of 47. Okay, very good. So getting back to the spreadsheet. So now we say, okay, we'll start with the combination of choosing out of 47 5 numbers, because this is the number of ways to choose the 5 winning numbers. But that's not the whole equation, because you also have the mega number. How many mega numbers can I choose from?
27.
27. Okay, very good. So we say multiply it by 27, and this is the total number of unique tickets. Does that mean that there are only like is it 41 million ish? Okay, so but we can actually sell more than 41 million tickets, because the lottos you can print duplicate tickets. Okay, so this is the number of unique tickets that can be generated from Super Lotto Plus. So what will become the chances of winning? Oh, by the way, this is also the cardinality of omega, right? Because omega is representing every single possible outcome. In this case, the possible outcomes would be a unique ticket of Super Lotto Plus. This is the total number of unique Super Lotto Plus tickets. So this is actually the cardinality of omega. Is that okay? So if we know this is the omega, the chances of winning becomes this number divided by this number, and then we should get the same number as published on the website. So we'll label this column. We'll shift everything down by 1 so that we have enough space later on to backfill the earlier ones. So insert 1 above, and this is chances of winning, something XYZ to 1. Okay, what is that XYZ? So this one is this number, which is the total number of tickets, unique tickets, divided by this number, which is the number of tickets that will win 4 out of 5 and the mega number. Should not be should not have a decimal point, so that doesn't look right to me. Okay, let me go back to the Super Lotto site and see what it has to say about this. 197,221, and I think we got the same number.
Yeah.
Yep,
rounded
we
up.
got the same number. So they presented. Okay, this is really tricky too. Not really a useful topic in a computer science class, but in marketing, it is going to be a really useful concept, because instead of telling you that your chances of winning is 0.000000 something, they're telling you that your winning chances is 1 in that number, which is basically reciprocal. Right? No? Kind of? Why do you think they want to do it like this? Instead of saying, okay, let me go to the spreadsheet, I can show you what is the alternative. Okay, this is 1 to XYZ. Okay, so I got it wrong here. 1 to XYZ, and XYZ in this case is 197,000 something, okay? So if I don't want to phrase your chances of winning like this, instead I'm saying, okay, but we have taken a discrete math class, we understand your probability, okay? So instead we'll say probability of winning, okay? That will become this number divided by this number, which is our P. Our P function is mapping from an element of F to a real number. And this is exactly what it is. Do you think it is wise to present this number on the Super Lotto Plus site? I think not. Okay? And this is not even small. Okay? This is not even small, because if I go all the way back here to say 5 of 5 and mega, okay? And what do you think that's going to look like? Okay. You already know it's 1, okay? But I don't like the number 1, so instead I'm going to use a different way to come to exactly the same value. Because in this case, you're dealing with a combination, because out of the 5 winning numbers, you have to get all 5. Right? Okay? What about the losing numbers? Out of the 42 losing numbers, you cannot get any one of those. Does that make sense? What about the mega number? You need to get the 1 that is the mega number, which is a 1.
There were 47 numbers, not 42.
What?
47 numbers, no?
Yes, but out of the 47 numbers,
Oh, yeah.
5 are winning numbers, and the other 42 are non-winning or losing numbers. Okay, so it all comes up to 1, okay, just like what we expected. Now let's go to the way to represent it here. So the Lotto site is saying that your chances of winning is 1 to this number divided by this number. Not very surprising, okay? But on the other hand, if you express the probability of winning, it is going to be this number divided by this number. It becomes the cardinality of the element in F divided by the cardinality of omega itself. Is that okay? And just look at that number, the number at D2, cell D2. Do you think that's a number that you want to publish on Super Lotto Plus, the website?
Not a zero in the wrong direction.
Yes, because there's a good population, who may have a problem understanding, okay, what does it mean when we have that many zeros before you actually have any non-zero digits? Okay? And it doesn't look very good either, okay, because you have a 2 after how many zeros? 1, 2, 3, 4, 5, 6, 7. There's 7 zeros after the decimal point. Okay, so there's a trick, okay? This is a trick of why these numbers are not, they are expressed in odds of 1 in so many instead of expressing the actual probability itself. Okay? All right. So let's go ahead and figure out the rest, okay? So we'll go back to the spreadsheet and figure out the rest. What about 3 out of 5 and mega? What do you think that number is going to look like? Okay, and just as a reminder, okay, this is way too much space, this much is good. So just as a reminder, this is how we figure out 4 out of 5 and the mega number. And the first one, is following the same pattern as well. Okay, so what do you think is going to be the equation for this one?
Combine 5 of
Combine 3
5 of 3.
3 out of 5, and the second combine is going to be 2 out of 42.
41.
No, 2 out of 42. You still have the
Oh,
same
yeah.
number of losing numbers,
Yeah.
but this time you have to choose 2 of the losing numbers instead of 1 out of the 2 losing numbers. And then times 1, because you still have to match the mega number. Okay? So you basically end up with something that's similar to the other one, but this time out of the 5, you're only choosing 3. Out of the 42, you're choosing 2 this time because the 3 and the 2, they have to add up to 5. Okay? And then also times 1, because you only have to match that one single mega number. Oops, syntax problem, because I forgot to type combine. There we go.
It was all caps.
I think it would take all caps too. Okay, there we go. And then we can try to come up with the same expressions. So I'm going to be a little bit lazy by putting a $ in front of these two so that I can just copy and paste. There we go. And the same thing over here. Oops. There we go. Okay, so let's check whether it's matching this number, 4,810. Yep. So it's all matching, very good. And then we can also look at this, okay. Oops, getting back to here. Okay, so this time we have 2 out of 5 and the mega number. And I'm just gonna be really lazy here, just change this 3 to what? 2. To 2, because we only need 2 out of the 5 winning numbers. Then we have to change this 2 to what?
3.
To 3, because we have to choose 3 of the non-winning numbers. And then the rest, we can just copy and paste now because I have fixed the, nope. Copy and paste, there we go. So it's 361, because we have to round up. Let's double check, 361, we got it. None of the 5, only mega. Okay, so that's kind of silly, but let's see whether our method works also here or not. So we have 1 out of 5 first, 1 out of 5, and the mega number. And we'll just copy and paste here. And what we are changing is this time we only need to pick 1 out of the 5 winning numbers, but then we have to choose 4 of the non-winning numbers to make up the 5 numbers on the ticket. And then the last one still has to be the 1 because we are still saying that we choose the mega number. And it's this number, so we copy and paste, okay? So it's 74-ish of winning, matching 1 out of the 5 numbers. And let's see whether that's the case over here, 74. So we got them all. Okay, and then there's the last one, which is none of the 5, only mega, okay? Do you think our pattern can continue? Okay, 0 of 5 and mega. Okay, let's check it out. Okay, copy and paste, and then we say, oh, we don't want any one of the 5 winning numbers. All the numbers that I have chosen are the non-winning numbers, and then times the 1 because I still want to match the mega. So we end up with this number. Let's go ahead and copy and paste these two and see if the numbers turn out to be correct as on the website. 48 or 47-ish. 49, oh, nope, 49 is right because I misread it. So this is 49, and it does match. So there's a 1 in 49-ish chance that you can win the least of all the prizes because you just matched the mega number. Is that okay? Okay, what about the other ones? I intentionally left some space here because this one is representing 5 out of 5 and not matching the mega. So what are the chances that I can do that? Or how many tickets will fall into this category? It's only matching 5 out of the 5 winning numbers, but it does not match the mega number. What do you think it's going to look like? 5, right? Because we need to match all 5 of the 5 winning numbers. Okay, which means how many non-winning numbers can I choose? 0. I don't have any non-winning numbers to choose. But then what about the mega number? How many ways can I choose the so-called mega numbers on my ticket so that I do not match the actual mega number? 26. Sorry?
26, choose one.
26, choose one, because, well, yes, because you're choosing one out of 26. Correct. So that it's exactly 26. And then we do the same thing over here, but this time we can just kind of, I have to choose this one. Okay, I can choose this one because it has no, the other one does not have any dollar sign, so it's not going to work. So in this case, the chances of winning 5 out of 5 is 0.000006277. That's the probability of actually getting a ticket that will win you the second best prize. Is that okay? And we can also kind of copy this all the way down here. And this one is going to represent 4 out of 5 and without the mega. So the only change we have to do compared to this one is we have to multiply by 26 instead of 1 because the other one has to match the mega number. This one is saying, okay, we do not want to match the mega number, which means we have to choose one of the other 26 numbers. So it's that number. And we'll double check and see if those numbers work out correctly. So this one is 7,500 something. So switch to the website, 7,500 something. So we got all the numbers. Okay, so we'll finish this table. We'll finish the entire table. So this is 3 out of 5, but without the mega. So we copy and paste this one over here, and then we have to change 3, 2 over here. Does that look right?
You accidentally edit the 2 of 5 and mega instead of the combined.
That seems right to me.
No, in the next one down.
You mean here?
No, in the 2 of 5.
You mean this one? 2 of 5, 42, choose 3. So this one should be right. Okay. But the numbers do not seem right to me. I'm missing something. Okay, this one's 3 out of 5. So we have 3 of the winning numbers, 2 of the non-winning numbers. And we are not matching the mega, so that there should be 26 left. If I switch back to...
Does that mean it's easier to win a 3 out of 5 than a 2 out of 5?
Yeah, it doesn't make sense to me. Because we should be getting 4,000. Okay, this is reporting 185. 3 of 5, 185. Yep, it is correct. It just didn't look right to me. Because I did not expect these numbers to be increasing again.
It means it's easier to get 3 out of 5 than a 2 out of 5 in a mega.
Yep, that's what it is. But the calculation is right. I was just doubting myself because I was expecting the numbers only to go in one direction. So 2 out of 5. So we just choose, copy and paste this one, change the 1 to 26. Okay. Yep, same pattern. It's not monotonic. So we copy and paste this one, change this one to 26. This is just matching 1 of 5. we go. All right. Are we missing anything? What are we missing here? Every single category, from row 2 all the way down to row 12, each row is representing the number of tickets that is winning something, right? What about all the tickets that did not win you anything? We haven't counted those yet. Okay? So can we use an equation? Can we use the equation that we have been using here to basically say 0 of 5 and not mega? Okay? What do you think that's going to look like? Combine 5, 0, right? Out of the 5 winning numbers, we did not get any. But out of the 42 non-winning numbers, we get all of those. Okay? We get 5 of those. Okay? What about the mega number?
Times 26.
Times 26, because we're not getting the actual mega number. Okay? And what do you think we should get when we sum up all of these numbers?
1.
We should, well, not quite 1.
The total number.
The total number, correct. It should be this cardinality. So let's check that, okay? Let's see whether that is the case or not, because this is a good way to double check to make sure that our calculation is in fact correct. I mean, that's telling you that it's right already, but it doesn't hurt to do the actual summation. Is that okay? So each row from row 2 to row 13, okay? Each row is an element in F, okay? In this case, I choose my subsets like this because I'm concerned about, okay, how many tickets is going to get the jackpot? How many tickets will get the first prize, the second prize, and so on. So I decide to break up omega this way. But the union of all of these elements in F, they have to add back up to omega. So this time we are just checking the cardinality, but the cardinality does match. Yep.
So row 14 would be the cardinality of omega?
Yes.
Okay.
Well, okay, row 14 is the summation of the cardinality for all of the subsets that we have, which is the same as the cardinality of omega. Row 16 is the actual cardinality or the calculated cardinality of omega. But it's good to double check and make sure that they are in fact the same. So is that okay? I mean, using Lotto as an example to illustrate the concept, sort of. So what do you get when you have 0 out of 5 and just match the mega number? What do you get? What is the price for that?
Nothing.
Price your ticket.
I think you get something, otherwise they wouldn't list it here, right?
I don't think they listed.
No, they don't look good.
Do they list, huh?
They don't list it.
Notified with mega.
They don't list with mega. They don't list without mega though.
Yeah, only mega. None of 5, only mega.
Yeah.
So if you match the mega, what do you get? Where does it say what are you gonna get? There has to be some place that will tell you what you're gonna win.
Why didn't it say play for 21 million this Saturday?
Sorry?
It says play for 21 million this Saturday. Is that?
Game details on the left.
Sorry? Details.
There's a game details under the in the ad.
On the left.
On the left.
Down below that blue stuff on the left.
Oh, okay.
Right there, below the blue stuff.
Below the blue
Right
stuff.
there.
Yeah,
Oh.
right there. See if that helps.
Okay. Oh, there we go. Price amount. So you do get $1 if you just match the mega. So you have about 1 in 20 chance that you might get $1, and then it costs you $1 to buy a ticket, right? Well, that right away kind of gives you an idea of is it a good idea to buy a Lotto ticket? So 5 plus mega is, so nobody won that, and it's a $20 million amount. And then 5, one person got 5 of all the winning numbers, and that person got $43,000. So how many? So on the average, how many tickets do you have to buy before you get one that will give you a 5? I mean 5 matching the first 5 numbers. There are 270 tickets, right? I think. And out of 270 tickets, let me. I keep using the tab here because it's actually a different tab in the browser itself. There we go. So this is the actual number you have to compare to. In other words, if you buy 197,000 tickets, you probably will get oh, I'm looking at the wrong number. I should be looking here. Wait. Okay, this is 5 only. Okay, there we go. So 5 out of 5. Yeah, it's not a very good. It's not a very good chance.
People don't win anything. I guess.
Yeah.
$1 back.
Yep. When you buy a ticket, when you buy a single ticket, there is a 53% chance that you may not get anything. That seems pretty low to me. Huh? That doesn't seem right to me.
Yeah, it doesn't seem right.
Yep. Yeah.
1 out of 5 doesn't win anything.
Say that one more time.
Just 1 out of 5 doesn't win anything.
1 out of 5.
Yeah, the mega.
Oh.
Well, this one, the numbers do not match. This one is way too small. So I messed up this number here somewhere.
No, but if 1 out of 5 doesn't win anything, it only wins if you get a mega.
Oh, okay.
So I think you have to add 1 out of 5 and 0 out of 5.
Okay, so we'll add this number and 1 out of 5, right?
Yeah.
So there's a basically 89% chance that you may not get anything for $1. Yep, I can think of better uses of my money. How much is a Raspberry Pi again?
$35.
$35? Okay, I think that's a better way to spend $35 instead of 35 Lotto tickets. Well, there you go. But I'll be kind of getting the idea of how the concept works. What omega is representing, what F is representing, and what P is representing. Is that okay? Cool. Yep.
Can you do like F equals a set of omega and comma omega? So there's like 2 of them.
You can do that, except it doesn't. It's okay. Yes, you can do it that way. It's just what do you get in return, right? Even using omega by itself, doesn't seem very useful because it's going to be 1. The probability of omega over omega is 1. So so you have to kind of think about yes, you can have F arranged this way. It's okay. It meets all the requirements, but at the same time, it doesn't have any practical use in this particular case. Yep.
How do you get the 4885?
The 48.
0.885.
Which row are we talking about? Row 13. Last one. This one? Oh, that's adding the non. There are 2 ways of not winning anything. These 2 are not winning anything. So you have to add the probability of 1 of 5 and 0 of 5 to get to the probability of not winning anything at all. And when you look at the tickets, so in this case, the total winning tickets is 114,000 something. Out of, does it say how many tickets were actually sold? Doesn't seem to show the number of tickets sold. Oh, it only shows you the number of tickets sold, but not it only tells you the number of tickets that are winning something, but not the number of tickets sold, unfortunately. But you can kind of guess it too. Okay? So looking at these numbers, how do we guess approximately how many tickets were actually sold? It's the ratio of the probabilities. Okay? So if it shows you right here, and you probably should pick a larger number because that's actually a more accurate way to do the estimate. So let's say, we look at 1 plus mega. And in this case, 35,000, let's just call it 35,000, 1 plus mega. So you plug that number back into here and say 1 plus mega is this number. The actual chances of winning is only this much. So what you do is you say 35,000, which is the actual number of tickets winning that particular prize, and you divide it by the probability of actually winning that prize. That will give you a rough estimate of how many tickets were actually sold in total, because the ratio would still be the same. So this is telling us that approximately 2.6 million tickets were sold in order to have this kind of distribution of prizes. Is that making any sense? Sort of? So you can actually use some of these numbers and go backwards and infer, what is the total number of tickets sold? And it's about 2.6 million in this case. So out of 2.6 million tickets sold, 114,000 tickets, got something. Yep.
So in this case, outcome is a two-tuple?
Yes. So each outcome is a two-tuple.
So it's not the fact that it's either a jackpot or a 5 at 5, it's just the fact that it's a two-tuple that is possible? So for all 5 out of 5, there's multiple ways to get one of those outcomes from that set F.
Mm-hmm.
So the outcome is just the two-tuple itself. One of the two tuples in that case.
Okay, each outcome looks like this. So this is this is what we chose to be the winning outcome,
Okay.
right? So when you look at each element of F, it is a set of outcomes. So when we look at this particular set, it is the set of all the jackpot tickets.
Yeah.
When we look at the second set, it is the set of all of the 5 out of 5 tickets. But each element in each set is still a two-tuple, where the first item of the two-tuple is a set of 5 elements, and then the second item is just a number. Because the first element or the first item of the two-tuple is representing the 5 numbers, but because order does not matter, it has to be a set and not a 5-tuple. The second item is representing the mega number, so it is by itself because it is independent to the first 5 numbers.
Would that two-tuple individually be a subset of the omega?
It will be, each one is an element of omega, yes.
Okay.
Yep.
Okay.
And then omega has what? We calculated what was it? So we calculated omega has 41 million, about 41 million elements. So are we doing okay so far with this type of analysis? Yep, go ahead.
Put this on Google spreadsheet.
The spreadsheet is already in my shared folder in cisp440. It is called Super Lotto Plus, but it's in the folder already. So if you go to that shared folder, you should be able to see it now. I'm kind of surprised that I don't see anyone actually on it right now. Any questions? Yep, go ahead.
Yeah, if you had duplicate elements in your F, so long as it still had omega in it, would it still meet the criteria for the union
Yes.
of it being okay?
Yeah, so the elements of F can overlap as long as the union of all of the elements of F, capture omega, is exactly the same as omega. It is still meeting all the requirements.
Okay.
In other words, you can say, okay, I want to look at things as, at least matching 1 number, at least matching 2 numbers, at least matching 3 numbers. So in that case, they're going to overlap. But it's okay because as long as, when you union all of the elements in F and you still come up with omega itself, it is still meeting that requirement. They don't have to be disjoint. Okay, good. Yeah, go ahead.
Is it easy to derive probability of winning if, say, 2 tickets were involved instead of just the 1 ticket? Like you have two chances instead of just buying one ticket?
If you have two chances of winning, then the analysis gets more complicated. Yep. And I know there are games in Lotto where you have a second chance of winning or something like that. Yep.
Wouldn't you just double your probability?
With a second chance of winning, but the second chance of winning is not the same as the first one, so it's not exactly doubling. It depends on the rules of the game. Yeah. And Lotto has so many different variety. My wife tried to explain to me because she and her colleagues will buy Lotto tickets to each other, despite me telling her about the probability thing. But they do it as a fun thing, so it's no more than just a social thing. It's like, okay, so here's a chance of retiring right now. So it's more of a tease than anything else. But there are but the rules of the games can be quite complicated. Any other questions about probabilities and whatnot? And just the terms, or the equations, how we use the equations. Do you guys see the regularity of these equations or these formulae? Yes, I'm hoping that we are starting to see a very definite pattern here. All right. So if there are no questions about this, we're going to move forward again. And you can see all the tabs that I have. Keep going. Keep going. Oh, there we go. We got it. All right, so after this, we are going to outcome, events, possibilities. We talked about that already. This is the one where we talk about this is the one right before the homework assignment that was extended to Tuesday. It's just defining what is an outcome, what is a trial, what is an outcome of a trial, what is an experiment, because an experiment is a sequence of trials. But when you perform a sequence of trials, then you have to you will run into a question, and the question is is it with or without replacement? What you have chosen out of one single trial, would that choice still be available to the next trial? That is the question of whether it is with or without replacement. Without replacement, it's a little bit harder to analyze. With replacement, it's easy. Okay? So trial with no restrictions, which is with replacement. So the question is, how do we generate the set of all the possibilities, the set of all the experiment outcomes? So it's actually pretty easy because, okay, so I have one example here. Okay, so let's say we're throwing a dice. Okay, so this example has to do with throwing a dice. Omega 1 is representing the possible outcomes of throwing the dice once. Okay, trial 1, throw the dice once. How many? What are the outcomes of throwing a dice a single time? 1, 2, 3, 4, 5, 6. Right? And that's why omega 1, the subscript 1, is indicating this is the omega of the first trial. What about the second time I throw the dice? What are the possible outcomes of throwing a dice a second time? Just the second time. 1, 2, 3, 4, 5, 6 again. All the way up to omega 4. Okay? So no matter how many times you're throwing a dice, the outcomes do not change. Okay? Unless you throw the dice so many times that the dice broke. Okay? Then you have some exceptional cases. So as a result, when you look at the outcome space of the entire experiment, it is really just the Cartesian product of the individual omegas. The individual omegas, omega 1 is representing the outcomes of the first trial, omega 2 is representing the outcomes of the second trial, omega 3 is representing the outcome of the third trial, and then lastly, omega 4 is representing the outcome of the last trial. So when you do a Cartesian product of these 4 omegas, then you have all the possible experiment outcomes for the entire experiment of throwing a dice 4 times. Is that making any sense? Okay. All right, so that's pretty easy. But when it comes to analyzing, the possible outcomes without replacement, then it gets a little tricky, because if you do it without replacement and you start off with 1, 2, and 3, and you choose one out of the first trial, then you only have 2, 3 left in the second trial. If you pick 2 out of the second trial, then you only have 3 left for the third trial. In other words, for the third trial, you don't really have a choice. It's going to be whatever is left. So how do you come up with the omega in this case? Now, dealing with the cardinality of omega is easy. We just use combination, okay, or permutation. But dealing with the actual set itself is a little bit harder. So in this case, I use a recursive way to do it. Okay, I'm not sure whether you guys look, when you look at this, do you see your program in it? I'm hoping you guys would see something here that resembles your program, especially with this one here. Okay, so let's take a look at this one. So this notation, omega x, comma, n equals 1, is representing, you start off, the first trial has everything in x that you can choose from. But the trials are without replacement. So once you choose something out of one trial, that thing is no longer available to anything else. And n is basically saying how many trials do we have to do. Is that okay? So when you have something like this, where you start off with x items for the first trial, and there's only one single trial, then the actual omega is just going to be x, because you don't have a second trial. Is that okay? Yeah. Okay, it's just a notation. And what if you are dealing with a case where n is greater than 0? Then what do? Then you have something like this. This is the essence of the program that you're writing when you have to handle the case of without replacement. It doesn't look like a program, but it is. How does it look like your program? First of all, is it recursive? It is recursive, right? Okay. Do you remember in your program you have a set subtraction? Do you remember you have a loop? And do you remember what you're looping over? What you're looping over would be elements of x, right? For each element e of x. That is the overall loop of your program. Inside each iteration of your program, what are you doing? You're saying, I'm picking e to be my element. For this particular trial, I'm picking e. Then what about the rest of these trials? I'll let somebody else deal with it, recursive, right? So when you do it recursively, do you remember that you have to pass a few important things over? What are you passing to the second, to the next iteration, to the next invocation of this subroutine? You have to pass the set, which has the element that you have chosen removed, right? So we have x minus the set of e. What else do you have to pass? The number of trials left, right? And that's n minus 1. What about PTR and what about start? Those are only for printing stuff purposes, okay? So we are not concerned about that when we're generating the set itself. But this is the essence of the program. Except it is not a program itself, it is a mathematical way to express what is the omega when you are dealing with an experiment that is without replacement. So is that okay or not? Because I'm trying to make you guys write a program because you have all taken cisp440. So programming is something that you are familiar with. This may not be something that you're familiar with. So I'm trying to associate something that you're already familiar with something that you're kind of learning at the same time so that you can associate an abstract concept to something that is a lot more concrete like C code. But that also comes along with all the bugs that can exist in C code. So is that okay? I mean, is everything tying in? Or do you kind of feel like these are all too fragmented and we have no idea what to do with all these different pieces? Okay, well, you can email me if you have any concerns, okay? If you feel like, tech is just giving us, a box of puzzle pieces, like 5 billion little pieces, and you have no idea how those pieces, fit together, email me and I will try to explain things in a different way. On the other hand, if you feel like, I can see how these pieces are being put together, okay, because I can definitely see, okay, now we can put these two things together, we can put these things together, then we are doing good. We are doing good in that case. All right? Cool. Okay, I'll see you guys next Tuesday. Have a nice weekend despite having 2 homework assignments for this class.